Hello. Hi everyone. So my name is Shubham Kataria and today I'm going to discuss what I did in homework 2 and I have chosen application focus. Uh, I've also used TensorRT as a video pipeline accelerator. I will discuss in detail about that also. So with the help of this chunk of code, we get to know if the GPU is available and what is the Keras version and TensorFlow version. With the help of this code, we get to know that is Ubuntu is available and what's it's the latest version and the CUDA compilation tools. We check if the NVIDIA SMI is present or not. These are some libraries which helps us to clone the GitHub TensorFlow models folder. We then install the setup.py file from the TensorFlow model uh, version. This is with the help of this, as you can see, we have downloaded the TensorFlow models object detection. Uh, wi- uh, this would be the labels, which provides the label pb.txt is a label file, which gives the complete classes with an ID present in that. So we have also given some test image to check if the downloaded model actually works or not. So we have downloaded an ResNet 50 Coco model. So this complete collab is of Professor, and it helped us to incorporate the new model and add an TensorFlow accelerator with the help of TensorFlow RT. So you can see that this is the object detection with the bounding box and the accuracy given. As you can see, the time is 7.165. This is also the second test image. Again, we have also used the mobile net detection as a different model. So for checking if our accelerator, which is TensorFlow RT, actually works on the given image, we have, or it is successfully installed. To check that, we have converted the ResNet model into FP32 TensorFlow RT model. Uh, and we have saved it into the saved model. As you can see, we have, for testing purpose, we can see that the last one was 7 point something, 7.61 or something for tensor for the normal ResNet model, which uses TensorFlow. But with the help of an accelerator, that is TensorFlow RT, we have achieved the uh, good performance, as well as it reduced our execution time, so which is 5.73. Also, to check for FP16, we have converted the TensorFlow model, which is an ResNet model, to TensorFlow RT model, which is an accelerator model. So as we can see that we have almost similar accuracy for the elapsed time for the FP32 and FP60. So it says that we have correctly installed the TensorFlow RT and TensorRT, and uh, the actual app pipeline is being accelerated. We have mount a drive here. Uh, this is XML to CSV conversion code. So whenever we annotate an images, we get an XML file. To convert that XML file to CSV, we need to perform some logic on that. So this is the code block for converting XML to CSV. Uh, I'll show you some of the images which I have used as a database for dataset. So this is the image in which we have annotated uh, the lamp, the bed, pillows, chair, plant, again lamp, and many such images are present. So in every image we have annotated, and there has been an XML document generated. I will show you the XML document in Notepad. So this is the XML document, and for training purpose, you can check what CSV we have got. This is actually the complete training uh, images. So we convert the complete training file to the complete XML files to multiple XML file to CSV, as you can see here. So this is the complete XML file that is converted to CSV. So then after that, we generate the TF records. For generating the TF records, we need the classes. So these are all the classes that are being defined. There are total 36 classes present. And this classes specifically gives us what is the boundary output line. Like if I annote the square box to a lamp or a plant. So this is actually written here. And the same ID is given, return 13. The same ID is given to label map.pbtxt. So this file consists of all the classes with the IDs given. So we can generate this. You can edit the file in Notepad and use it as for the purpose of label maps. So after running this code, you have successfully created the TF records, and we are saving the TF records into this file, which has test.record and train.records. So to check if they have successfully created or not, we have used the below code block, which says that it has been generated into the TF record files. So we are checking here, like check TF records, if they are correct or not. So we have successfully checked the TF records, and we are we have also included the train path in which the TF record is given, and the image size is 640 by 640. And after that, we downloaded the ResNet 5050 model, and that tar is been unzipped here. We have created my output folder. So we can see we have just displayed the pb.txt file here. After that, we can see the configuration for which we have done the batch size as 2, and the model name chosen is faster RCNN ResNet 50 underscore 640. 640 says that we have used an image of size 640, so we have chosen this model. So this is where we generate the pipeline, and it's all configuration. So we are taking just a single checkpoint right now. So that would be the checkpoint 0, and accordingly it would be generated. Many more checkpoints would be generated again. So these are the two TF records, that is test and train. We can change the pipeline configuration whenever we want. After running this code, the pipeline config is being generated, and in that also we need to change the batch size. That was 64, but then we need to make it as 2. After that, we have trained the complete model on our own data set. It took around 40,000 steps to run, around 2.5 hours. We are running it using the Collab Pro. So it took around 2.5 hours to completely uh, run the model. After running the model, I have seen that this many checkpoints are generated with their specific index file. After that, we then the new exported models dot faster RCN dot zip, the file is being downloaded. The model has been downloaded, which is trained on our data set, and we have tested accordingly. This is the TensorFlow board. So I have taken YouTube video, and so with the help of PyTube, we have downloading the YouTube video, and that YouTube video, we are moving it again to test video 1.mp4. This gives us how much time of the video do we want to have, a complete video clip 1. So I've chosen here as a 4-minute video. After this, we can see that the elapsed time is 8.64. We have again included the label map.txt. We are importing the video clip and its size, like what is the frame width and frame height. With the help of this code, we are completely annotating each of the bounding boxes into the running video. This is an real-time video processing. We give an video as an input, and we get a video with the bounding boxes and accuracy as an output. So we can check here without the TensorFlow RT. This was completely based on without TensorFlow RT. So it gives us the complete elapsed time is 100.09, and the frames processed per seconds are frame per second are 18.57. So after that, we have generated the output video one. I can show you the output video. So this is the before TensorRT, as you can see. Uh, so it's correctly calculating the pillow, the bed, again the complete bed and pillow. So I've taken this is as in 2 minutes of I've cut down the video for just 2 minutes as it was for 4 minutes. So it's correctly detecting the frame, the lamp, the pillow, the bed, as we have annotated the images in that kind. So this is a real-time video bounding. You can, with the help of, you can input any video of bedrooms, kitchen, or any persons. You can get the running time, uh, the live bounding box video onto the object. But we so currently we have chosen the video which suits our dataset. So right now my dataset consists of an bedroom images and bedroom frame images. So that I have taken that. So this was without the TensorFlow RT. We can also give an input through webcam. This is the complete code of webcam. I have found this code onto one of the GitHub libraries. I've given as a reference to that code also. So after right now we will be installing the TensorRT for accelerating the video pipeline. So we need to check if our version there is a Ubuntu version present or not. So we have downloaded the NV TensorSort repo Ubuntu, this one which has the .debian as an extension onto our Google Drive, and I'm unpackaging that file, installing some of the dependencies for Ubuntu. After the successful installation, I'm installing the PyCoda, and we can check here different versions of the complete grape TensorRT. So we are converting our model to TFRT F32. We can just change it to FP16 by just writing down FP16 here, and the new model will be saved into application focused TRT. So after saving the output, the same process, the same code is being utilized, and we can see that the total time elapsed is 90, as it was 100.09. I've also written the conclusion. The total time required without the TensorRT was 100.09, but after TensorRT, it's 98.24. So it makes sense because we are using the TensorRT as an accelerator by using NVIDIA CUDA platform. So this is the complete real-time based video. The real-time based video is given, and you get to know the bounding boxes accordingly. So this is so we have completed the real time. Again, we have applied the TensorFlow RT, which is used as an accelerator for video pipeline. We have used our own data set, which constitutes of many images, which has the bounding boxes and annotated the different images. Uh, this is the folder for the complete new exported file. And we have the pipeline config file here. I'll try to open it into the notepad. So as you can see here, this is the config file, and I've changed the batch size to 2 in this, as it was 64 and it wasn't able to execute. So you can see that the train config has the batch size 2. So this is the video before TensorRT, and this is the video after TensorRT. Let's take a look at the video after TensorRT. It's just a YouTube video which is downloaded with the help of PyTube. As you can see, we get the accuracy as fast as possible, and the bounding boxes are being accelerated because this is the version with the TensorRT. So we have achieved all the guidelines which are given for the homework too, which says that we must use our own data set with the existing model and utilize at least one of the accelerator. The TensorRT references actually helped me to achieve that. So that's it from my side. Thank you.